All right, so section 9.6. This is the ratio and root test. Now in this section, the homework that they give you, they're going to tell you a couple times like, okay, do these problems using the ratio test, do these other problems using the root test, and then there's going to be a section of homework that says, okay, just figure out if these converge or diverge, which in other words, now it's up to you. You get to look at what it is and decide, should I do the nth term test, geometric, p-series, should I do ratio test, root test, direct comparison, limit comparison, integral, alternating series, what should I do? Right? So now that's when it starts to get a little tough because you got to say, well, what do I have? Like, what are they giving me? How can I figure out which test works best? Okay. I will still always tell you, check the nth term test for divergence first, no matter what, because if it works, then you're done. Right? After that, then you got to worry about what should you try. But we're going to start off with the ratio test. Okay. So let me give that to you guys. This is theorem 9.17. And by the way, these tests are not that hard to do. Okay, so the ratio test, I do like these. They're not too difficult. But it says, let the series A sub n be a series with non-zero terms. And there's three things that could happen. First one, the series A sub n converges, actually converges absolutely. If the limit as n approaches infinity of the absolute value of A sub n plus 1 over A sub n is less than 1. The series diverges if the limit as n approaches infinity of the absolute value of A sub n plus 1 over A sub n is greater than 1, or the ratio test is inconclusive if the limit as n approaches infinity of the absolute value of A sub n plus 1 over A sub n is equal to 1. In other words, the test doesn't work, you better try something else. So a lot of people say, oh, this is a lot like the geometric series test, or it kind of reminds me of the p-series. Well, yeah, but with the p-series, you need it to be bigger than 1 to converge, right? Whereas with this one, you need it to be less than 1. So it's a lot more like the geometric series, right? Where you're looking for less than 1, right? So converges absolutely. If the limit is less than 1, it diverges. If it's greater than 1, and if it's equal to 1, it's inconclusive. Now remember, A sub n plus 1 basically means you're going to change your sequence by a plus 1, an n plus 1 term. Okay, so it's not terribly difficult, like I said, to do this. A lot of people actually don't mind it, but thank you. They are sometimes time consuming, not too bad. Turn that in. All right, so let me give you guys some examples here. Okay, so example number 1. The sum as n goes from 0 to infinity of 2 to the n over n factorial. So I don't know if you guys remember, but the last lesson that we did, we had some problems like that, and we were supposed to check to see if they were absolutely convergent, and I said we can't do them yet, so we're just not going to do those, right? So we needed the ratio test to help us with this. So in order to do this, what you're going to do is you're going to take the limit as n approaches infinity. Now I'm going to do this the way that they write it at first, and you're going to notice like, wow, that looks really bad. And then I'm going to flip it the next time, but you'll see what I'm talking about. So let's do a sub n plus 1, okay? A sub n plus 1 is 2 to the n plus 1 over n plus 1 factorial divided by, that's a sub n plus 1 on top, okay? And then a sub n would be 2 to the n over n factorial. Now you see how ugly that looks right there? It's just, the fractions is just a huge compound fraction. So next time I'm going to write a sub n plus 1, and then I'm going to multiply by the reciprocal of a sub n. That makes it a lot easier, okay? But that's actually my next step. My next step is going to be limit as n approaches infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. Now I'm going to take this a little slowly, okay? I want you guys to kind of see it at first. Now you should be good at doing this by now, they assume, right? But if you haven't done it in a while, you might forget. So let me break this down. This is an extra step. Usually I will not show this because it is kind of a waste of time for you guys to do it, but maybe you need it. 2 to the n plus 1 is the same as 2 to the n times 2. Are we okay with that? Because 2 is 2 to the first, and if you do 2 to the n times 2 to the first, you just add the powers because they have the same base, right? So it's just like saying x squared times x cubed, we write x to the fifth, right? So 2 to the n times 2, which is 2 to the first, would be 2 to the n plus 1. Okay, again, they're assuming you guys got this, no problem. Now, you notice how there's an n factorial on the top right corner, but on the bottom left, it's an n plus 1. I want those factorials to match, so look what I'm going to do. I'm going to write n plus 1 times n factorial. I just removed one of the terms from the factorial so that they match. And then on the right side, I'm just going to leave it the same, n factorial over 2 to the n. Notice I can now cancel. Okay, I can get rid of stuff, so my limit as n approaches infinity of, on the top it's a 2, over, on the bottom it's an n plus 1. Now before I move on to the answer, are we good? Uh-huh.
In the first fraction, we have n plus 1 times n factorial. Where did the n factorial?
N plus 1. Oh, so remember, n plus 1 factorial is actually written as n plus 1 times n minus 1 times n minus 2, etc. Right? You always the next term is always subtracted by 1. Now you can keep writing this out till you're done. 3, 2, 1. Okay? But if I just want these two things, this right here, to match up with this, all I have to do is exclude one term. Notice from here to here, that we would write as n factorial. So I just excluded one term, and then I rewrote the rest of it as a factorial. So I just broke it down. And then from there, I was able to cancel. So what's my limit? 0, which is less than 1. So what can I say? It converges absolutely, right? So I'm going to write that the sum as n goes from 0, right? It was 0, yeah. 0 to infinity of 2 to the n over n factorial converges absolutely by the ratio test. So the ratio test is not like really hard to do based on definition. The hard part with the ratio test is you're going to have to know how to break down your function so that you can cancel some stuff out. All right? And if you can't do that, then it's really hard to use the ratio test because the ratio test demands that you understand how to break down factorials. It demands that you know how to break down powers of n, right? N plus 1, that means you have a power of 2 to the n plus 1 means that you have a 2 to the n. but then an extra 2. A 2 to the n plus 2 means that you have a 2 to the n times 2 times 2, right? There's 2 more bases in there. So they want you to be able to do that. Okay, let me erase this little piece. It is in the video if you got to watch it again. I'm just going to erase it because I don't want you guys to think that you had to do that in order to do the work. Okay, so let's try another one here. So example number 2. Let's see if we could figure this one out. So the sum of n squared times 2 to the n plus 1 over 3 to the n. All right, so this one doesn't look like it's going to be easy, but again, it is easy. You just got to break them down properly. All right, so here we go. Now, remember what I told you guys. I do not want to write a huge compound fraction. So what I'm going to do is I'm going to write a sub n plus 1 and then multiply it times the reciprocal. That's the same, okay? So n plus 1 squared times 2 to the n plus 1 over 3 to the n plus 1 times the reciprocal would be 3 to the n over n squared times 2 to the n plus 1. Now again, I'm going to take this slowly. I want you guys to at least see it twice. After that, we'll just take we'll do canceling the way most people will do the canceling. But let me simplify this a little bit. Limit as n approaches infinity of n plus 1 squared. I'm just going to leave it alone, okay? That's just a polynomial. I'm just going to leave it alone. Now, you see how 2 to the n plus 1, that's really 2 to the n plus 2. You guys with me on that? So that's the same as writing 2 to the n times 2 times 2. That's what 2 to the n plus 2 is. Because that's n plus 1, right? Right here, a plus 1, plus 1. So that's n plus 2. Okay? Divided by, well, the bottom, I can rewrite it as what? 3 to the times 3. Right? And then the other one, you don't really break down too much. 3 to the n is there, n squared. And then 2 to the n plus 1, I'm going to write it as 2 to the n times 2. And now let's start canceling stuff out. All right, so let's see. I can cancel out a 3 to the n. I can cancel out a 2 to the n. I can cancel out a single 2. I cannot cancel out the n squared because it's not the same term, right? But I canceled out a bunch of stuff, so let me rewrite this. This is equal to the limit as n approaches infinity of, let's see, on top I have 2 to the n plus 1 squared. On the bottom I have a 3 and an n squared. What's my limit? Two over 3. Which is less than 1, which means that this, not the limit, the series, as n goes from 0 to infinity, of n squared times 2 to the n plus 1 over 3 to the n converges absolutely by the ratio test. Notice the ratio test is more of a test to see if you know your algebra than it is to see if you know your calculus. Right? Like you really are like using your algebra skills to say, how can I break this stuff down? I need to break it down or else I can't figure it out.
For the homework, you have to find the RT and do the ratio?
No, because then you have root test. Yeah. So some of them, yeah, you can use like the alternating series test, AST, if you want to. Now on the AP exam, please write the whole name, okay? Because they might say, I've never abbreviated. What is AST, right? So always use the full name, but in other cases, it doesn't work. All right. Now, I'm going to show you an example that diverges, but it's going to result in a trick here, and I think you guys should be able to do it, but we'll see. I think you'll be able to do it. It's just sometimes some people don't see it, but we'll go through it. Okay, example number 3. And remember, if your limit comes out equal to 1, it's inconclusive, which means try a different test. Okay? We're not going to do one of them that equals 1, but it's easy to tell when it's going to equal to 1. Just erase the 2 over 3 in this problem, and that would be a 1, right? If you didn't have a 2/3 on that limit above, then it would just equal to 1, in which case you say, can't do it, I need to try a different test, okay? But I want to do one that diverges. I want you guys to see a divergent one. So we're going to do this one right here. The sum as n goes from 1 to infinity of n to the nth over n factorial. So again, limit as n approaches infinity of n plus 1 to the nth plus 1 power over n plus 1 factorial times n factorial over n to the n. Remember, I multiplied by the reciprocal of the sequence. Now let's break this down. Again, I'm just doing this right now, just so you guys get a little bit of practice. But maybe when I go over the root test next, you'll see like, okay, I'm gonna have to do this one by breaking these things apart using some algebraic stuff. But for now, n plus 1 to the n times n plus 1. That's n to the n plus 1 to the n plus 1. Okay, so there it is. N plus 1 to the n times n plus 1. Now, n plus 1 factorial, I noticed that I have an n factorial on the top right corner of that first fraction. So I'm going to make a match. So I'm going to write n plus 1 times n factorial. I don't know if you see it, but I can actually cancel out my n plus 1s right now. Okay, so it's actually working two purposes. And then n factorial over n to the n. So the things I can cancel are n factorials, n plus 1s. Uh-huh.
Why can't you take out an n factorial and n plus 1?
Well, it's kind of like this. If I told you 5 factorial, it's 5, 4, 3, 2, 1, right? You always subtract 1 from it, right? You could also write it as 5 times 4 factorial. That's 5 factorial as well, right? Or you can write it 5, 4, 3 times 2 factorial. That's still the same thing. Well, it's the same with, let's say, n plus 2 factorial. You can write it as n plus 2 times n plus 1 times n minus 1, etc. You can write every term if you want. Or choose to just take out 1 or 2. So you could choose to write it as n plus 2 times n plus 1 factorial. Or if you needed an n factorial so you can cancel it out, you could do it like this. And that's still the same. Because you're still saying I'm going to multiply the previous term and the term before that as well. So it's still an n plus 2 factorial. I'm just reworking it so that maybe I can use it to cancel things out. So let's see, the limit here is now limit as n approaches infinity of n plus 1 to the n over n to the n. Okay? So a lot of times people will say, oh, well, that's equal to 1, so it's inconclusive. Okay, but that's actually not true. The reason is there is a definition that the limit of this, let me rewrite it a different way. N plus 1 over n to the n. That right there. That's actually equal to e. So this is a definition you guys are going to learn right now. Okay? That the limit as n approaches infinity of n plus 1 over n to the nth power. Now, some people like to write it as 1 plus 1 over n. This little thing, they like to write it like this.
Why is that equal to e though?
That's actually its definition.
But like,
There's a proof for it, and if you want to see the proof, again, see me later, or when you take math theory in college, if you decide to, you will learn about it. But yeah, it's one of those theorems that they don't expect you guys to know, but they do want you guys to memorize this, just in case you see it on an exam. Okay, but that's equal to e, and notice e,
it's 2.5.
yeah, that's greater than 1. So this diverges, right? So the sum as n goes from 1 to infinity of n to the nth over n factorial diverges by the ratio test. So yeah, please memorize that definition. It may not come out on your calc test, but if it does on your AP, at least you'll know that the limit as n approaches infinity of n plus 1 over n to the nth is equal to e. Now, like I said, usually I would stop here and say, like, okay, tomorrow we'll go over the next one, but I'm not going to be here tomorrow. So I'm going to kind of teach a little bit longer right now. And I apologize for that. I usually don't like to do an all-period thing. I'll try not to go all-period, but we do have to do the next test, okay, which is called the root test. So this is theorem 918. And by the way, it's not that much more different than the ratio test, which is kind of nice. But it's called the root test because you're going to be using an nth root. Okay? So it starts out the same way. Let the series be a non-zero series. So let this be a series with non-zero terms. In case you're wondering, what the heck does that mean? In other words, none of the terms have a 0 in it. So it doesn't go like 1, 2, 3, 0, 4, 5, 6, 7, or it doesn't start with 0, 1, 2, 3, 4, 5, 6, 7, etc. Fractions, 1/2, 1/3, 1/4, 0. That doesn't happen, okay? Non-zero terms. So something is there, a concrete number that's not 0, okay? This has 3 steps in it, just like the other one. Okay, and you're going to notice they pretty much are almost identical in definition except for the how you test it. So the series converges absolutely. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. So you're going to take the nth root of it. Now people always say, well, when do I know I should do this? Well, if you see an nth power, an nth root usually knocks it out, right? So sometimes when you see a lot of nth powers, you'll use this test. Okay? Second one, the series diverges if the limit as n approaches infinity of the nth root of the absolute value of a sub n is greater than 1. So notice, same definition as the ratio test, just a different way to test it, right? They're using the nth root. And the third one, you can probably guess, the root test is inconclusive. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to 1. And I'll show you 2 examples here. All right? And what you'll like about this is usually they're relatively quick. They're not as long as the ratio test. And even the ratio test isn't that long, but not as long as that. Is anybody still writing the theorem? All right, go ahead. Like I said, these will go pretty quick, so I don't want to do it real quick and you're still writing.
Like, because of how it worked, I was just like, for the first one I wrote out the whole thing, and for the second one I just said, if greater than one diverges.
Yeah, just do just write the limit part and you'll have it. You'll have it. All right, so here we go. We're going to test to see if this converges or diverges. That's e to the 2n over n to the nth. Now you notice how that has nth terms in the powers, right? 2n on the power, and then the bottom is n to the n. So that's kind of a dead giveaway. If they both have nth powers, then I can also rewrite it like this, right? N goes from 0 to infinity of e squared over n to the nth, right? You guys know we can do that, right? We can extract a power that they have in common and make it all inside that power. So check it out. Now that I did that, let's find the limit as n approaches infinity of the nth root of e squared over n to the nth. What's the result of that? It's e squared over n, right? By the way, you notice I didn't put it, but I'll put it right now. I'll put the absolute value. I didn't do it because there's no negative 1 to the n in the front. It's not alternating, so it doesn't really matter, okay? But if it is alternating, then I would have done it. In this case, it doesn't do it. So the limit as n goes to infinity of e squared over n, what is that equal to? 0, right? And 0 is less than 1. So then I can say that it converges absolutely. And we're done with that one. So the sum as n goes from 0 to infinity of e to the 2n over n to the nth converges absolutely by the root test. Now, it doesn't mean that only certain things work with the root test, only certain things work with the ratio test. You probably could have done this with the ratio test as well, but it might have been a lot harder. Okay? But usually n to the nth power, you want to use a root test on it, but not always, because in example 3, we used a ratio test with an nth to the nth power, right? So it just depends. You have to kind of do these things enough where you're like, no, I remember these don't work in this situation. Let me try something else, right? Enough practice will get you there. So let's do one last one. I think we'll still finish before the bell's gonna ring, but like I said, I just want you guys to have everything you need to know, because tomorrow I'm gonna make you guys do some homework in class that I want you to turn in, and then you're gonna have some homework to do when you go, okay? So here's example number 5, last one. As n goes from 1 to infinity, n plus 1 over 2n plus 1 to the nth. Okay? So, we're going to try using the root test, and it's kind of a giveaway here too, because notice everything is raised to the nth power. Right? So what gets rid of an nth power? Well, an nth root, and that's exactly what the root test tells you to do. So let's do the limit as n approaches infinity of the nth root of n plus 1 over 2n plus 1 to the nth. And again, I'm going to put the absolute value there, but it's actually not going to affect the problem because it doesn't get rid of any negatives or anything like that. So what do I get when I take the limit of, or when I take the nth root of this? All right, over 2n plus 1. So what's my answer?
Oh, I understand what the answer is.
Okay, so it's a half, which is less than 1. So then this converges absolutely as well. So the sum as n goes from 1 to infinity of n plus 1 over 2n plus 1 to the nth converges absolutely. Yeah, I'll show you right now. So this nth will get rid of that. Yeah, so that'll get rid of that. So converges absolutely by the ratio test, by the root test. Sorry.
If you can figure out why the absolute value is
Why?
Because -5 would be less than 1, but because it's also greater than 1 on the negative side, the absolute value is there, so that it.
Correct.
Why?
Yeah. And remember, you also shouldn't have your negatives inside of square roots or nth roots and stuff, right?
Yeah,
So,
'cause if you get imaginary numbers.
yeah, and we don't want that stuff. So, all right. So let me stop this recording here.